All right, so as we vary the height that we allow an object to fall, we will measure the time it takes to fall that distance. Does anybody know what theory suggests in terms of how is the time it takes an object to fall related to the height, like how high up it is in a gravity field? Does anybody know how that's related to gravity? Anybody? How is height related to time? If you give an object more of a chance to fall, it's going to pick up speed, right? The acceleration due to gravity. So that's definitely true, right? So we'll pick up velocity. So we can kind of think about getting a lab out of this as the speed, the final speed of something is related to how fast you let it fall. But so too should the time be, right? Like if you let it fall from higher up, it's going to take longer to fall, right? How are those related though? Is it just like directly proportional? Is it just like height directly proportional to time? This little fishy symbol here is proportional to. Is that how it goes? A linear increase in this? Or is it related to the time squared? Yes. H equals 1/2 t squared. Well, that's not fair. We've never used that before. Except for like, oh, crash course in it. Remember that? Right? That's how they're related. Okay? We want to get a lab out of this. What do we want to calculate? What do we want to determine? Okay? We already did that. We did pendulum. Right? When the pendulum oscillated, we found local G. Yet another way to determine local G, dropping things from heights and measuring how long it takes. All right? So we're going to generate a plot of this quantity against that quantity. 7 data points, best fit line, do some analysis, set the slope equal to that. Now, if y'all want to work with the equation just the way it looks right now, in other words, we could turn this into like y equals mx. In other words, just keep it the way it is now. And then we want to plot like the heights on the y-axis, even though it's the independent variable. We usually plot the independent variable on the x-axis. The thing that we're going to vary, right? I'm going to move these photogates. So, all we really care about is the distance between those photogates. Like as the marble drops through these, I'll have in my recorder here how much time it took to fall through that height, even though the marble's going to keep falling, right? As I vary this lower one, what am I changing? H, right? So as I vary the height, you all are predicting it's going to take more time, right, for the object to fall between these photogates, okay? And we'll know very accurately how much time it took. So as I place that in there, you know, my fingers sort of break the photogate timer and start recording time to neutralize it. If we leave the equation the way it is now, then we're sort of going to make a plot where we're going to plot these varying heights on the y-axis against the time squared on the x-axis, right? So our sort of graph is going to look like We're going to plot height, measured meters, against time squared. Everybody can see that the problem. Measured second squared. Time squared measured in second squared. And then, once we plot our data, we find the slope. What are we going to set the slope equal to deduce G? We plot height on the y-axis, time squared on the x-axis. What's the term that says how does this quantity vary to give us, this output? 1/2 G, right? So I go, what one? That's just a number. 1/2 of 9.81. The number that we multiply the time squared by tells us how high we are. So if we plot data, we can use the graph itself to find the slope of the best fit line. We'll have data points, find data points, and then we'll know the slope, right? By actually doing a calculation on our graph paper. We will then set that slope value equal to 1/2 G and solve for G. All right, that's our conclusion. The claim we want to make is G equals however many meters per second squared. Because we're plotting height against time squared, look how the units give us the units of acceleration. Rise over around meters per second squared. Okay, so we get the right units for acceleration. The other thing that we can do with this is make it look more like last week's lab. So let's make t squared all by itself. So t squared equals what? What is t squared equal in terms of this? H over G, right? We're gonna call it that. We probably want to write it like this stuff. 2 over G times H is how we said. 2 over G times H. And then we have like this would be our y. We just plot t squared on the y-axis against the heights, and then it's more like science. Like scientists tend to plot the independent variable on the x-axis. But there's no rule that says we have to. Like we're gonna sort of plot the convention. And we're just say, hey, we're gonna plot the dependent variable on the x-axis because we can. Don't gonna stop us. Now, if you don't feel good about that, feel free to plot this. Okay. And then you'll set the slope equal to 2 over G and solve for G. Right? In other words, the height times 2 over G gives us t squared. So you plot the data as you see fit. You're like, I want to stick with the convention of plotting the variable on the x-axis. What's the thing we have control over? Not the time. That depends on the height, right? We control the height of the photogate. That's what I'm varying. As I vary that, I will measure the time, and I'll square it. So for a data table here, I hate to erase the fundamental forces of the space here. If we already measured G potential now, what's the point of? Why would a scientist be interested in like independent method to arrive at the same conclusion? It builds our confidence if we get the same result. Independent method, whatever that was. Do an experiment, reach the same conclusion 5 different ways, and all those conclusions agree with each other, build our confidence that we got the right answer. We don't really have like a textbook, with all the answers in it as doing research. Sort of have to rely on our cleverness, our ingenuity, different experiments. Give that a moment to try. All right, so I'm going to be as precise as the instrumentation allows me to be. I'm going to vary the height. I'm going to measure the time with my photogates, and then you all will calculate the time squared as I report these values to you. How many data points do we want? 7. We're always going for 7 data points. Now, I'm going to vary this over the greatest range possible. So with the apparatus I have, I can move this down to like 1, 2, 3, 4, 5, 6, 7, hopefully. And as this distance gets greater and greater, we're sort of relying on a true sort of drop there for the ball. So I have this mechanism to release the ball. If I drop it, I go off center. It really is important that the diameter of the marble breaking the photogate. Things, photogate have to be sort of flush with the back of this if they were sort of at an angle. And let's say only a sliver of the marble broke the photogate. It's going to record much less time, and we're going to get results that indicate it's dropping much faster than previous, right? Because the whole marble didn't break the photogate. I mean, that whole distance. So sort of the islets here are right in the middle of this. Another thing that scientists have to make a judgment about is like, well, what is the distance between these things that have thickness? Is it from the top of this to the bottom of this, from like the bottom of this to here? How do I measure that? The important thing is whatever you decide as the scientist, as the person doing the experiment, this is how I'm measuring it, you always measure it that way. And I was like, well, this time I'll measure from here to here, and the next time, why not from here to here? Like, be consistent in what you do. The center to the center, that's a good rule of thumb. Like from the center of this, or like, where is the measuring time? Like the little islet is right here. Oh, I got it. Exactly 5 centimeters. It's like, it was 5.1, I would call it that. 5.0. 0.05 meters. .05 meters. The height. Up here. And time in seconds, and you all will get the time squared and second squared. Remember, we're going to plot this on the y against this on the x. Draw a best fit line through our 7 data points. Set the slope equal to 1/2 g. Solve for g. That will be your claim. We're expecting an answer of 9.8 thereabouts. All right. Trial number 1. 0.06187. 0.06187. See what I think is a stopwatch for this lab? .0618 squared is, come on, you learners. Look at the next one. Look at the next one. All right, I'm going to vary my independent variable here, guys. And note that I've adopted a procedure where I'm just going to keep this one right there, right below the catch, or beneath the release mechanism, and I can just vary this one down, right? So I'm increasing like even though it's dropping the same height, right? I'm only measuring between here and here. So it's like effectively giving more displacement sort of fall through it. If you did this lab without photogate timers, we have to go outside. Even if I like stood on a ladder and dropped something from the top of the ceiling, okay, and we use stopwatches to time it, Earth accelerates things pretty quickly, right? And so something will fall from the top of the ceiling and hit the ground in less than it takes less than 1 second. That would be 15 meters up there, or 5 meters up. About 3 meters to the ceiling. Exactly. Pretty good job varying the independent variable. .2 centimeters. 0.122. Always try to keep consistency in your data tables like this. Like, so if I have 0.05, which is exactly 5 centimeters, I should really say it's 0.050 meters, right? If I'm going to record this as 12.2 centimeters or 0.122. I want this to have 2 digits. 0.1146 0.1146 and 0.1146 squared is, none of those voices came from this. What is it again? 0.013. All right. Let's vary the independent variable. Yeah. It's about as fine as it gets in science now. Vary the independent variable. That's it. All right. Enter. $20. 22.8. And I am writing diagram chalk. No mistakes. Okay. It's 0.1778, but I want to test it. I'm going to veer off course a little bit there. 0.1777, pretty consistent. Okay. Press it. Close. And 0.1777 squared is, I give a chance. What is it again? 0.0315. All right. 3 data points. Let's get more. Let's get 4. $33 even. All right, at 33 centimeters drop height, the time is, what do we need that again? That's 0.2262. .2204. One more time. 0.2209. So that sounds about right. 0.2209 squared is all right. So that's 4 points for the in person, 0 for the ignorers. They're still bad. They're still bad on this one. I wish I could do something about that. That's very independent variable. Last day. 43.4. Yes, precise as the instrumentation allows you to be. So don't just round it to 43.5 because it's close. If it's 43.4, measure it as such. At 43.4 centimeters of drop height, mortal, okay, maybe 0.2603 seconds. Seven, 5, 3. I mean, like as this height gets greater, there's more motion there. Still. 0.2640. Remember that number, 0.2640. Point 2610, I felt good about that. 0.2610, 0.2604. Okay. 0.2604 squared is, everybody with a calculator knows that 0.2604 squared is, really? The independent variable. 0.5. 0.5 centimeters, right? 100 centimeters per meter. Into the metric. 0.3126. 0.3126 squared is the last data point. Six. 70.6 centimeters is 0.736 meters. And we can measure that a marble that falls at distance in Earth's gravity field will take, oh, it made it in the catch too, 0.3533 seconds in the roll. 0.533 seconds. It's good that we've established a trend that, like, as we've increased the height, so too has the time increased. There's no violation of that trend here. So we kind of can just, upon inspection, look at the data and go, yeah, we would expect it to fall. I mean, it could be like there's curve or sort of plot here. In fact, if we plot this data, we would see it. That's why we plot time squared. We want a straight line. Okay, in other words, we want sort of this. Here we suggest this to be true. If it is, we should be able to measure this as we vary this in order to determine G. All right, claim G equals whatever you get by setting the best fit line of this data. If you want to use this data, feel free to do a stopwatch type lab if you can, measure things from, have to be high enough up that, the stopwatch uncertainty isn't going to affect your data too much. So, like, even inside of it, if we drop things here, it'll be like, maybe what we do is start it, hit the ground, stop it, and there's a lot of human reaction time with uncertainty in measurement. So feel free to conduct this experiment safely, okay, by reaching ever greater heights safely. If it's too high up in Earth's gravity field, the wind resistance really will be a factor. Okay, so it's like, oh well, I'm going skydiving, this afternoon, and all the time, it's not going to work. Okay. So feel free to use this data here. What was this? Okay. Say it again. 0.1248. So there's a complete set of 7 data points. Remember, if we plot this on the y against this quantity, I'm not extending out of my mind if I lost this today. Everybody else is hearing them like that out too. The phone's ringing? this is your X quantity, this is your Y quantity, and then set the best fit line, you know, the slope that you can calculate, right, from your data, what will happen. Okay? So that will be your claim. Your evidence will be C plot, right? So it needs to be a graph for 60 out of your 100 points, right? And then the reasoning is going to be because theory suggests, remember where this comes from. This is from your equations of motion, right? So we kind of derived a form of this equation. Because theory suggests this, I can get a lag out of it. I can use it to measure G. That's how we can start to think as physicists. Like, you know, here's sort of a suggested relationship in nature, and I can actually put it to the test. That's what science is about, not just trusting, you know, like what some philosopher says. It's about testing something in the laboratory, right? Figuring out for ourselves empirical evidence. All right. With that, I will